Hello, I'm Frank Sanders, Senior Technical Fellow at the Institute for Telecommunication Sciences, ITS, the NTIA Laboratory in Boulder, Colorado. This ISART talk is on 5 GHz Dynamic Frequency Selection DFS technology development and deployment, challenges that have been met, and lessons that have been learned. Development of unlicensed wireless access systems WAS in industrial, scientific, and medical bands at 5 GHz began about 25 years ago. The problem with putting unlicensed communications into ISM spectrum at 5 GHz is that primary radar spectrum allocations overlap the ISM spectrum there. The solution has been to find a technical method to allow spectrum sharing for WAS unlicensed National Information Infrastructure UNII devices in 5 GHz spectrum, and, along the way, to ensure a spread of WAS traffic loading across the 5 GHz spectrum to reduce aggregate WAS emission levels down to the required levels for fixed satellite service and Earth exploration satellite service EESS compatibility. When the work began at 5 GHz, there was a precedent that had already been constructed for use in the industrial, scientific, and medical ISM band, stretching across 2400 to 2483.5 MHz. There, unlicensed IEEE 802.11b and 802.11g WAS systems were already operating at 2.4 GHz. In that spectrum, there were unintentional but relatively high-power microwave oven emissions that were already occupying that spectrum. The microwave oven emissions look a lot like regular radars. This suggested that a similar spectrum sharing approach might be possible in the 5725 to 5875 MHz ISM band. But the parallels were not absolute. The 2.4 GHz ISM band does not overlap any licensed spectrum. This differs from 5 GHz ISM bands that do partly overlap licensed allocated radar band assignments. Between 5250 to 5850 MHz, there are allocations for radio location and radio navigation radars that include radio location on a primary basis, radio navigation on a primary basis, ground-based meteorological radars on a basis of equality with stations in the Maritime Radio Navigation Service, and between 5650 and 5725, radio location on a general primary basis. There were also some perceived constraints on 5 GHz WAS. For example, 802.11 device regulatory requirements and band allocations varied widely around the world. This produced manufacturing difficulties for 5 GHz WAS across national boundaries. It was believed that any requirement to produce many different varieties of 5 GHz WAS to meet all of the varying 5 GHz spectrum requirements from one administration to the next would place an undue manufacturing burden on developers. To address these issues, an ITUR recommendation M.1652 was developed through many ITUR administrations between 1999 and 2003, notably in Joint Task Group 8A-9B and in Working Party 8B, now Working Party 5B. The document that came out of all of that work, M.1652, is still the root technical document for 5 GHz DFS. A purely technical aspect of what had to go into that recommendation was the power level at which the wireless device emissions would cause interference into the allocated radars at 5 GHz. In response to this, ITS in Boulder and the Office of Spectrum Management, NTIA's office in Washington, D.C., jointly launched a fundamental research program into the levels at which RF interference will cause various types of radars to lose targets. The summary of all of that work is that radar targets tend to begin to be lost when interference levels from non-radar signals in radar receivers are 6 decibels below the noise level of the radar receivers in question. Substantial losses occur when RF interference equals radar receiver noise levels. This work was documented in separate ITUR recommendations and also in NTIA Technical Report TR-06-440. Some particular features of M.1652 deserve to be noted. These came out of WARC 03. For example, 5250 to 5350 and 5470 to 5725 MHz bands are allocated to the mobile service on a co-primary basis with the radio determination service, provided that devices in the mobile service in these bands use dynamic frequency selection DFS sharing technology to protect radar receivers from interference. WAS and Radio Local Area Network RLAN operations are not to cause interference to radar receivers. DFS-equipped devices operating at 5 GHz are required to detect local radar signals and avoid the occupied radar frequencies through constant monitoring of radar signals while also sending and receiving their normal wireless radio traffic. In M.1652, representative characteristics of 5 GHz radar systems in the band are described. The required thresholds for detection of radar signals for signal avoidance by the WAS systems are determined. Requirements are presented for determining channel availability by monitoring spectrum prior to the use of a 5 GHz DFS channel, and speed requirements are presented for vacating DFS channels when radar signals are detected above critical detection threshold levels. Domestically, in the United States between 2003 and 2005, the FCC, NTIA, the Department of Defense, and UNII industry participants worked together to develop certification test plans and procedures for DFS devices to operate in the 5250 to 5350 and 5470 to 5725 MHz bands. Prototype testing followed in 2005 and 2006. This was 4 to 5 years after initial technical work for development of DFS protocols had occurred. The prototype testing was to involve bench tests with prototype DFS devices that would be sent from multiple manufacturers to the ITS laboratory in Boulder, Colorado. At the ITS lab, radar transmitters replicated radar waveforms as defined in M.1652, which were specially built by ITS engineers, would be put into DFS systems to verify that the DFS systems could successfully detect and avoid the radar signals. Then, later in December of 2005, radiated field testing against actual radars was performed at the McGregor Range next to the White Sands Missile Range in New Mexico. In the 05-06 timeframe, 2 rounds of DFS testing were initially completed. There were some difficulties with DFS detection of radar waveforms that were noted in this initial testing. DFS performance improved during the second round of testing. Along with NTIA, the FCC and the U.S. Army participated in all of this testing. 2 goals were accomplished overall. First, it was shown that DFS devices could actually detect radar waveforms as specified in M.1652, and the test and measurement setup that could be used by the FCC and later by independent certification laboratories across the U.S. was validated through the actual certification initially of DFS devices at the Boulder Laboratory. In this time frame, specifically in 2006, NTIA transferred its DFS certification hardware and associated custom-written test and measurement software to the FCC's Columbia, Maryland laboratory for use in further certification testing and, as noted, for eventual transference to the private sector for ongoing certification testing. Here's the flavor of what had to be done in this testing. First, there had to be verification on power on of a DFS system that no DFS emissions would occur for 60 seconds after initial power up. This system has to remain quiet after the on button is pushed for at least 1 minute. Any radar signals present when power on occurs had to be detected within 6 seconds. And radar signals have to be detected 6 seconds before the end of any initial channel check time by a DFS device. Then, when a device is running in its normal mode, various synthesized radar waveforms have to be detected in the 5 gigahertz bands in what's called in-service monitoring. This involves the most comprehensive testing for DFS UNII devices, and it does not precisely replicate, this is worth noting, any particular exact operational radar waveforms. There are problems with detecting exactly what certain radars produce. What we have to do instead is show that the device can detect across a parameter range of radar waveforms, including a range of pulse widths and a range of pulse repetition rates. Operating across these ranges ensures, first of all, that there's no problem with needing to divulge classified material about radar waveforms, but it also means that the DFS devices cannot be precisely tailored to exactly detect exact radar waveforms, which themselves might vary in different times and places in the future anyway. And then finally, in the certification series, there's a 30-minute non-occupancy test that we have to show is successfully passed. This test is used when a DFS channel has been occupied by a radar signal. Once that channel is occupied by a radar signal, the UNII device is not to attempt to use the channel again for at least the next 30 minutes. Here's a quick table of some other parameters. The detection threshold requirement for DFS receivers is either -62 or -64 dBm in the receiver circuitry in a 1 megahertz bandwidth peak detected. The exact number is specified in the Code of Federal Regulations for certain circumstances. The availability check that has to be employed before any channel can be used is 60 seconds. 60 seconds of off time, quietly listening before a channel can be used, and if a radar turns up in that 60 seconds, then the channel cannot be used. If a channel has been occupied and the radar signal is detected in the channel, then the channel has to be vacated and may not have any attempted reoccupancy for the next 30 minutes. The maximum interval that's allowed for the channel move after radar detection is 10 seconds. In other words, if a radar pulse is detected in an occupied channel, then that channel has to be vacated within 10 seconds. Within that 10-second interval, the maximum sub-intervals that are allowed for housekeeping transmissions inside the UNII device is 200 milliseconds plus about 60 milliseconds available for various particular operations over the course of the 10-second overall vacation time. To do all of this, NTIA engineers in ITS in Boulder had to come up with a compliance test bed. This included a radar signal generator and synthesizer that would produce bursts of unmodulated and chirped radar pulses in the subject 5 gigahertz bands. It had to have a variable and user-selectable set of options for radar pulse frequency, number of pulses to fire in a burst, pulse width, pulse repetition interval, chirp, which is linear FM bandwidth, and RF power control for the pulses. A vector signal generator that was programmed by ITS was used to generate these pulses. On the UNII side of things, there had to be a monitor for RF activity on a UNII channel by a UNII system. This used and uses a vector signal analyzer and a spectrum analyzer for both fine and coarse measurements of the RF emissions of the base station and client transmissions over 12 seconds at a time. Both the radar and the DFS systems had to be synchronized so that the press of a button would start the in-service testing and collect data continuously for 12 or 24 seconds on a common time base. This slide shows a block diagram of the overall testing system. The development of the system and its transference to the FCC initially and to the private sector in the U.S. eventually was a major accomplishment of the overall effort. This slide shows a photograph of the system as it was assembled at ITS and was used in initial testing at the ITS laboratory as a prototype. And so, about 6 years after formal development of DFS protocols began in mid-2006, DFS-capable UNII devices were finally made available to consumers in the U.S. A wide variety of DFS-capable 5 GHz UNII devices were soon certified by the FCC and by independent labs and marketed by several manufacturers. Along the way, NTIA itself undertook random off-the-shelf spot checks of commercially available products employing DFS technology to verify that the DFS functionality was in fact present in the marketed devices and was working. But in 2008, NTIA and the FCC discovered a certified product that was not detecting radar signals. It turned out that after the product had been marketed, there were post-certification changes that were made to some of the UNII device's firmware. The changes were not supposed to affect the ability to detect and respond to radar pulses, but unintentionally, the changes did, in fact, effectively disable this device's firmware from detecting radar pulses. It was also discovered through spot checks that there were some additional issues with certification identifications of some devices' responses. Basically, what it amounted to was that some devices that had been certified in the laboratory as being successfully able to detect radar pulses, and which did have their DFS functionality intact in the marketed products, were sometimes not detecting some radars in actual field situations. In particular, by early, which is to say January of 2009, the FAA, Federal Aviation Administration, was reporting interference to its 5 GHz microburst warning weather radars, and the interference appeared to be coming from DFS-capable 5 GHz UNII transmitters. Subsequent NTIA, FAA, and FCC studies, some conducted in Puerto Rico, others in New York, and which were performed with the help and the cooperation of manufacturing industry participants, identified some DFS devices that had passed the certification tests, but that were not adequately detecting radar signals in the field from the terminal Doppler weather radars operated by the FAA. At this point, government and industry worked together to improve the parameters for the certification testing. While this was going on, further certification testing of new 5 GHz DFS-capable UNII devices intended for outdoor use was temporarily suspended altogether, pending development of some revised certification testing parameters. The essence of the problem overall was this. Way back in the formative stages for the technology, when inquiries had been made as to the exact technical parameters of the radars that would need to be detected at 5 GHz, there was a disconnect that occurred at the human level between the actual parameters of the radars in the band and the set of parameters that was made available for the testing. This disconnect resulted in the original initial certification testing not always using the actual parameters of radar pulses that were operating in the 5 GHz band. Straightening the problem out lasted from 2009 until about 2010 or maybe even 2011, when we finally were able to implement a revised set of test parameters that unequivocally did cover the parameter range of the actual radars operating in the 5 GHz band. In terms of challenges met, here's what it amounted to. The first technology for DFS was eventually successfully deployed and is now operational. The 5 GHz spectrum is now widely used by a variety of commercially available DFS-capable UNII products produced by many manufacturers and shared with a lot of radars. But to get there, close cooperation was required between government and industry. Substantial effort was required to determine interference protection criteria, the levels at which radars had to be protected for the incumbent service, that is. And about 6 years were needed from the initial DFS concepts as they were initially sketched out to the marketed devices that were eventually sold to consumers. This included time to formulate DFS protocols as embodied in Recommendation M.1652, time to develop and verify certification compliance testing, hardware and software, and development of DFS protocols that had to be agreed to by government and industry before any DFS-capable devices were built. Lessons learned from development of all of this included timelines that are needed for converting spectrum sharing concepts into marketed devices can be 5 years or longer. This includes time that is needed to develop protection criteria for incumbent service receivers, developing engineering spectrum sharing protocols, developing spectrum sharing protocols and rules, developing spectrum sharing compliance certification, hardware and software, and performing initial test and evaluation of prototype devices. Beyond that, government resources may be needed on an ongoing basis to perform spot checks on marketed devices for compliance with spectrum sharing rules in government spectrum bands. Substantial attention has to be devoted to ensuring that field performance equals laboratory performance during certification testing. In other words, this kind of spectrum sharing is not shoot and forget. This kind of spectrum sharing requires ongoing spectrum engineering and compliance testing for as long as the spectrum sharing is going to happen. It can be regarded as the cost of this kind of spectrum sharing. It does grow the economy. It does offer opportunities for manufacturers and consumers to use spectrum that would otherwise not be used. But it is a continuous maintenance mode that is required when dynamic spectrum sharing is implemented in any given band. We conclude with a set of references that may be instructive to anyone who wants to further inquire into the processes involved that we've discussed here, the lessons that have been learned that we've discussed here, and I thank you for your time.